Today we'll be doing the integral from 0 to infinity of the inverse tangent of e to the minus x dx. And to start, we could rewrite this integral as the integral from 0 to infinity of the inverse tangent of j e to the minus x, where j is going from 0 and j is equal to 1 dx. So this is equal to the integral from 0 to infinity and the integral from 0 to 1 of the partial derivative with respect to j with the inverse tangent of j e to the minus x dj dx. So this is equal to the integral from 0 to infinity and the integral from 0 to 1 over 1 plus j e to the minus x squared times the derivative with respect to j of j e to the minus x dj dx. So this is the integral from 0 to infinity, and then the integral from 0 to 1 of 1 over 1 plus j e to the minus x squared times e to the minus x dj dx. And from here, I reverse the order of integration. So we have the integral from 0 to 1, the integral from 0 to infinity, e to the minus x divided by 1 plus j e to the minus x squared dx dj. So we now have that our integral is the integral from 0 to 1 and the integral from 0 to infinity of e to the minus x divided by 1 plus j e to the minus x squared dx dj. And to start off, we'll make a substitution. So I'll let m equal j e to the minus x, which means that m over j is e to the minus x, which also means that the natural log of m over j is negative x, which also means that the natural log of m minus the natural log of j is negative x, which also means that x is negative ln m minus the natural log of j. So x is ln j minus ln m. So we take dx, we have dx is 0 minus the derivative of the natural log of m. So we have a minus 1 over m dm. And that m sub 1 will be j e to the minus 0, which will be a j, and m sub 2 be j e to the negative infinity, which is approaching 0. So m is from j to 0. Okay, so we have everything we need to make the substitution. So we have the integral from 0 to 1 and the integral from j to 0 of e to the minus x, which is m over j, 1 plus m squared times dx, so minus 1 over m dm, and it was dj. So as you could see, this will cancel. We have a 1 over j, so it's the integral from 0 to 1 of 1 over j, the integral from j to 0 of minus 1 over 1 plus m squared dm dj. But because of that negative, we can reverse the order of integration of the bounds. So we have the integral from 0 to 1 of 1 over j, and then the integral from 0 to j of 1 over 1 plus m squared dm dj. But this is a standard integral. It's the integral from 0 to 1 of 1 over j, the inverse tangent of m from m is equal to 0 and m is equal to j dj. So we have the integral from 0 to 1 of 1 over j inverse tangent of j dj. So we now have the integral from 0 to 1 of the inverse tangent of j over j dj. And if you recall the power series of the inverse tangent, we have tangent inverse of j is equal to the sum from 0 to infinity of negative 1 to the k j to the 2k plus 1 over 2k plus 1. So is equal to the integral from 0 to 1 of 1 over j, the sum from 0 to infinity, negative 1 to the k, j to 2k plus 1 over 2k plus 1. And we'll exchange the order of summation integration. So you have the sum from 0 to infinity, negative 1 to the k over 2k plus 1. Integral from 0 to 1 of 1 over j times j to the 2k plus 1 dj. But it simplifies into the sum from 0 to infinity, negative 1 to the k over 2k plus 1. The integral from 0 to 1 of j to the 2k dj, which is equal to the sum from 0 to infinity, negative 1 to the k over 2k plus 1 times j to the 2k plus 1 over 2k plus 1 from j equals 0 to j equals 1. But this is just the sum from 0 to infinity, negative 1 to the k over 2k plus 1 squared. And this is known as a famous constant called Catalan's constant. It's denoted with a g. So in the end, we have that the integral from 0 to infinity of the inverse tangent of e to the minus x dx is g, Catalan's constant. And this is the final result.